Welcome back to the EXD. Last week we took our first look at LLM inference using vLLM. More specifically, we learned about the prefill and decode phases of an inference pass and how their performance characteristics differ. This week we'll dig a little deeper and make our first attempt to tune vLLM for better performance. My name is Ram and I work at the Ethereum Foundation on internal AI ops, and this is an open learning log for what I call the EXD. If you're new here, check out episode 1 to know what the EXD is all about. I'll link it in the description below. Okay, on with the show. First, a quick recap. In episode 3, we looked at the anatomy of an LLM inference pass, and essentially the user's text input is first tokenized, and these tokens are then passed through the LLM in two phases: the prefill phase, then the decode loop, and finally the text output is delivered to the user. We generated a benchmark using vLLM's inbuilt benchmarking tool, and we got a very simple benchmark that looks like this. We saw some tokens per second per user, what the total token throughput was, and some other statistics. And we basically introduced ourselves to the world of benchmarking inference performance on an AI server. This week, let's dig a little deeper and more specifically try and understand how we can benchmark the prefill and decode phases separately, because we understand that their performance characteristics are different. And for this, we'll use something called Llama Benchy. So Llama Benchy is a tool, open source tool, the repo for which I'll link in the description below as well. And this actually lets us benchmark prefill and decode separately, amongst many other things. We've got Llama Benchy working. Let's get it set up with some common arguments. This is basically just the server URL, which model we're going to test, etc., etc. So let's just get that out of the way. And let's do a quick smoke run just to understand what it looks like. So I'll talk through these parameters as it runs. So this runs Llama Benchy and says, listen, send a single user. Let's simulate it failed. Let me just try this again. Sometimes it does that. Let's clear and run this again. Let's see if it starts. And it has started. Okay, perfect. So we're saying, let's just assume there's one user. Send the prompt length, which is going to get pre-filled. That's what this PP is. Should be around 128 tokens. And the generated tokens length should be 256. Depth will come to later. And just do one run of this. That's essentially what this run is going to be about. And we got the results already. And we see here that with a single user, the prefill is processed at 360 tokens per second, and the token generation actually proceeds at 42 tokens per second. And this is expected because the prefill actually can pass the entire incoming prompt through the GPU in one go, as we saw last week. And that's the prefill phase. And in the decode phase, the LLM actually produces it one token at a time, and the token is appended to the original prompt, the KV cache reads are done, and we pass through the token through the LLM once more. It produces a new token that gets appended, and so on and so forth. So as expected, our decode speed is much lower in terms of tokens per second, because it's a sequential process, an auto-regressive process that has to proceed in this manner. Whereas prefill is actually a completely simultaneous process where the entire prompt is fed in one go. Okay, so this characteristic of decode especially leads to some potentially, at least it was for me, counterintuitive observations about how LLMs work under concurrency. So let's quickly look at a concurrency scaling demo and see how multiple users affect the token generation speed. So once again, I'll run this and then explain what we're doing here. It's the same as the last one. We're doing a pre-prompt length of 128 tokens. The token generation output is expected to be 256. But here we're saying the concurrency should be 1, 2, 4, and 8. And we're just going to do one run of this. So what Llama Benchy is going to do is the first run is going to be exactly like the run we just did, where it's just a single user sending the single prompt and expecting a single output, and we're going to see what we get. Then it runs it again with 2 users, and they run their prompt simultaneously, then 4 users, and then finally 8 users. So what we're doing is we're just hitting the server with an escalated number of concurrent runs, and here we see the output. Let's pull this out so we can see it clearly. So this is the first run. This is the results of the second run, that is concurrency 1, concurrency 2 users, concurrency of 4 users, and concurrency of 8 users. And we notice something kind of interesting. As we increase the number of users, it looks like our tokens per second is increasing. So in the first run, where we just had 1 user, we had a processing speed of 522 tokens per second through the prefill phase, and then 48 tokens per second through the decode phase. But when we increase the users, the concurrent users, to 2, we got 406 on prefill, but decode speed actually moved up to 75 tokens per second. For concurrency of 4, prefill has now increased to 658, and decode has increased to 80. And finally, under a concurrency of 8 users, we actually get 1,454 tokens per second and 146 tokens per second for decode. So what's going on here? Shouldn't any resource, when it's hit by more and more users, actually slow down? To understand this, let's take a look at our simulator. And this is sort of the main thing that we're going to learn about in today's episode. These systems are not made for single users. They're actually made for serving concurrent users. And that's what they're actually optimized for. So if you remember, this is our simple simulator. It's our pipeline view, and it talks about how with a single user, say somebody comes and says the cat sat, how it gets tokenized, and only the RAM and the CPU are active, and then it enters the prefill phase in one go, and then there's a decode loop where the GPU is active and the KV cache is active, and it keeps looping until it gets to the output. Let's look at the same thing with another toy example, but this time with multiple users. So this is sort of a multi-user concurrency tab. And we have 4 users, A, B, C, and D. And they're all going to sort of hit the GPU at slightly different times. So first we start with user A, and they start with the standard, the cat sat kind of example. And the GPU is idle. Their prompt is getting tokenized. In the next tick, we have now entered the prefill phase, and user B enters. Now we have the CPU handling the tokenization of user B's prompt, and the GPU meanwhile has started the prefill for user A. Let's proceed some more, and let's just say for user A, the prefill continues while user B is waiting a bit. And in the next tick, and remember, this is just sort of a made-up toy example, but just to give you a sense of what the dynamics look like. In the next tick, user A has entered the decode stage. the GPU is still active, KV cache is now activated, and user B has entered prefill, and a user C has entered, and their prompt is just getting tokenized at this stage. We move forward, and maybe that person now user C is waiting, and user A is continuing in the decode step, user B is continuing in prefill, and the next tick, both A and B are in decode, user C is waiting, and the user D has entered, and the CPU is now tokenizing their prompt. And if you proceed further, perhaps A and B are now both in decode, user C is in prefill, and user D is waiting. You get the picture. This is actually a dynamic environment. And vLLM is actually doing a lot of juggling to handle multiple users and try to saturate the GPU as much as possible. And in fact, in the next step, this is what we see. A, B, C, and D are all sitting on the GPU now. The first three, A, B, C, are in the decode stage, and D is in prefill. So what's actually happening here with a single user is you're not necessarily saturating the GPU when you enter the stage. And because it's a sequential process where prefill has to go in one pass, and then decode has to generate just a single token and go back and run everything over again, and you can't kind of go to the next step until this pass is completed, it's not obvious that you have saturated the GPU's capacity through each run. That's actually only possible under multi-user concurrency. And this is actually why we see that as you increase the number of users, you can finally get to a stage like this where the GPU is firing at full capacity and generating tokens across the board. Okay, this was obviously a very hand-wavy sort of toy sketch of what's going on. But Llama Benchy is really the right tool to sort of dig into this more deeply. Okay, so we know this, that we can add more users and start increasing the performance of the LLM. Let's start trying to improve this now. So in this episode, we'll basically look at just two knobs. And in vLLM, there are two flags, max num sequence and max number of batch tokens, which actually can help us do this. Max number of sequences is basically the maximum number of concurrent sequences that the GPU will process at one time. So you can actually, so for example, if I set it to 1, then everything is going to process sequentially. User 1 is going to come, they're going to get completely processed, and only after they're done will user 2 start. That's basically what 1 is. And 2, 3, 4, and 5 will look more like the simulator that I just walked you through. And the max number of batch tokens is basically a dial that lets you decide how many tokens are actually batched when the GPU processes any user. So once again, if your max number of batch tokens is small, then you can stuff a lot more users. So if you have sort of workloads in which you have many users asking very short questions, for example, you can make the token size small because you know that you're not going to get some big chunky thing, and you can service multiple users at one time. Yeah, and let's look at setting up a baseline first so that we can decide how to improve things, or just so that we can even like set a benchmark against which we can start improving our performance. So to do this, let's look at the model that's running and the flags that are running right now. So this is now the AI top atom. We have switched to the AI server. Let's go to the EXD directory. In fact, let's go to the projects and serve directory, because that's where the action is on the AI top atom. And if you remember here, we had a couple of scripts which let us run the models and a set of configs for running models with different flags. And there is a model currently running with the baseline flag. That's what is running right now. So if you look at Docker PS, this tells us what containers are running, and yes, a container appears to be up. This container is currently running the baseline configuration. So let's take a look at what that looks like. So cat configs and quen 3.6, and let's look at the A3B. 35V A3V baseline config. Okay, so there's a couple of things to note here. It looks like the same model we served last time. We have told vLLM to limit the GPU memory utilization at 80%. We have told it that, and we've basically not really specified anything else that's relevant to us. We'll get to these other parameters later. But essentially, this is running sort of a baseline config of vLLM. So let's test how well this does under concurrency. In fact, we already did, but let's just run it again. But this time, save the results into a model so that we can compare them later on. So let's get back from the Atom to LlamaBenchy. We have already done this. We are at, we have already exported the common arguments. So now let's run this benchmark again. And I'll, like last time, I'll start it and then walk you through what we're doing. We are doing running LlamaBenchy with prefill sizes that sweep from 512 to 2048 tokens in length. We expect less than 256 tokens generated as output. We're going to do 3 concurrency setups: single user, 2 users, and 4 users. And we're going to do 3 runs of this, and then finally save the results here. That's basically what we're going to do. And we'll just let this run through. And in fact, I'll actually return when this is done. See you guys in a sec. And we're back. So let me just make sure that we're back. Yes, we are. Okay. So the run completed, and it saved the results. But let's just understand what just happened. So LlamaBenchy ran the following runs. First, it did the combination of 512 and 256 prefill and decode. So the prefill, that is the prompt entering prompt size, was 512, and the expected output was 256. And it ran that against batch size 1, that is concurrent users 1, concurrent users of 2, and finally 4 concurrent users for this combination. Then it switched to a larger prefill size with the same target output. So this time 2K tokens entering and 256 coming out, again for a single user, 2 users, and 4 users. And this is the kind of response it gives you. I made a little convenience script to visualize it. This is what it looks like. So on average, when the prefill for a single user at 512 was 1626, and as expected, with 2 users we went up to 1728. With 4 we went up to 2264, and the decode proceeded from 44 for a single user to 66 with 2 users up to 78. Similarly, for the combination of for when the prefill is 2048, we got these results, and they're actually very similar to the first pass. So that's what we're looking at here as a baseline. So what we've done is we've just done a single run, and we're saying this is what we're looking at if we do no tuning of the model at all. So how can we improve this? And this is sort of a perfect time to do a small segue and talk about what we're doing in the EXD. I mean, the goal is to work backwards from an objective and use that objective to sort of motivate our learning. Instead of like learning a bunch of theory and slowly building up to the kind of models and inference engines and other things, that we use in work today, I kind of wanted to go backwards. Start with a somewhat production-like setup, a cutting-edge model, and give ourselves an objective like this. Improve the performance of serving Qwen 3.6 35B using vLLM. And then work backwards to understand what we need to learn in order to actually achieve this. Okay, so back to this. We can start with tuning one very simple and sort of easy to understand knob, which is GPU memory utilization. So if you remember, let me quickly switch back to the AI top atom here. We are currently looking at, well, let me ls the configs here so that I can get the name. This is the model, this is the current baseline that we are running, and this is what it looks like. Configs. If you look at this, just ignore all the other flags. This config says cap the GPU memory utilization at 0.80. So what if we turn this knob up? How's it going to affect our numbers? Let's take a look at that. So to do that, first let's bring our currently running server down, and we do that by running the down script. And let us then pull up a new config. So this is going to be sort of this standard config over here. Let's see what it actually looks like. And all this pretty much does is it increases the GPU memory utilization to 0.85. So here it's 0.80. Sorry, here you can see it's 0.80. Let's bump that to 0.85 and see what it does to our to Llama Benchy. Okay, there's a couple of other changes that we're doing over baseline. We're going to say the maximum number of sequences at any one time are going to be 16, and the maximum number of batch tokens is going to be 8K in length. So those settings are also over here. You can see them. They've not been set over here. Cool. So how do you run this? You basically use the up script. So go to scripts, up.sh, and well, not getting this. We are now going to run this model. So this will once again take some time to spin up. So sorry, I made a mistake over here. I don't need the .env. You should just run it with just the name of the file. So let's run it properly. There you go. And now let's look at the logs. There. Let's give this a couple of seconds to spin up, and I'll meet you guys back here when it's done. And we're back. So vLLM is now started up with our new configs. Let's make sure that container is running. Yes, it is. So let's run our benchmark again. So just to remind ourselves, we have now spun up vLLM again. We have bumped the memory utilization. We have increased the number of sequences that can concurrently be processed, and also the number of batch tokens. Alrighty. So to run this, let's go back to Yoneda, and let's basically run the same benchmark again, and save it to a different file. So we're going to do two prefill sizes, 512 and 2048. We're going to use the same target output size, 256 tokens. And we're going to do a concurrency of 1, 2, and 4 with 3 runs for each, just like we did last time. This is going to take a second again. So I'll meet you guys back when it's done and we can discuss the results. Okay, our new run has now completed. Let's see how we did. Let's pull up the results for the new profile. Oh. Okay, simple error over here. It's just profile, not this thing that was repeated. Okay, so once again, we have two sets of prefill, 512 and 2048, which we ran against 1 user, 2 users, 4 users, and these are the results that you see. The numbers seem to have increased a little bit. So if you remember, well, let's see what we have got in the profiles actually. So cat, the temp directory, and oh. All right. So we basically got these two profiles that we run. This is the baseline profile, and this is our conservative profile that we just ran. Let's just refresh our memories on the baseline profile. So that was Quen 30. Quen 36 for some reason. Let's call this. That's just the JSON file. Let me use the script to visualize it. Sorry about that. So this is our benchmark viewing script, and this is the run that we just did. These are the results, and what we actually need to do is pull up the baseline script and just take a look at it. So that looks like this. This is the baseline script. Okay. All right. We see that it looks very similar for the single user, almost no difference, but it's a little faster for concurrent users. So if you look at this, the baseline is a teeny bit faster for a single user, but then you got 2 users. Our tuned profile is just a little faster, 67 versus 66. And for 4 users, actually it becomes a little even more faster. And similarly, for 4 users on 2048 prefill token length. The baseline gave us 78 tokens per second, but the tuned version with more GPU headroom and max number of sequences and batch length is actually at 86. Okay, so we have started sort of increasing the performance of vLLM, and we started understanding how a sort of a knowledge of the internals can help us work with these flags to start improving performance. Let's just push one more knob. Let's just turn one more knob before we call it a day on this episode and see if we can push this any further. So let's take the GPU utilization up to 0.88. Let's increase the max number of sequences to 32, and let's also increase the size of the max number of batch tokens. To do that, let's first go back to the AI top atom. Let us bring the currently running model down. And once again, let's look at the config that we need to run to pull this up. So this is more for speed. ls configs. Let's look at this config. This is called a throughput config. So what does that look like? Cat config / let me just copy that. Okay. GPU memory utilization is at 0.88. The max number of sequences we're going to allow is 32 this time. And the size of the batch has been increased to 16K tokens. Okay. Let's run this. So to run it, we use the scripts again. So we go scripts up and then the name of the config. Once again, this was going to take a minute to come up. So I'll meet you guys back here when it's up and ready to benchmark. Okay, our new server with 0.88% GPU memory utilization, max number of sequences of 32, and 16K batch size is now ready. Let's make sure it's still running. There you go. Let's run Llama Benchy against this configuration and see if it can improve on the previous one. So let's do that. This is the throughput profile. We're running the exact same 512 and 248 test. Let's run it. This is once again going to take a second, so I'll meet you guys back here when it's done. Okay, the benchmark is now done, and let's see what the results look like. Made the same mistake again. We do not need this prefix. There you go. Okay. Looks like not so much of an improvement. It'd be better to sort of compare these runs against each other. So let me pull up these commands. So first, let's look at how we improved on the baseline versus our first attempt. So this is the baseline run results, and this was the first conservative short run. The name appears to be wrong. Let's get the names right. Okay, so ls/temp/ okay, so the names are Quen 3.6, but it says 3.6 here. All right, and the baseline one is called Quen36 35. That looks fine. Okay. So I think what was missing was the 3.6. There you go. These are the baseline numbers, but they look a little janky. Let me just tune this and just fix this formatting and come back. Sorry about that. This is actually much cleaner. So what we're looking at is the comparison of the baseline run versus our first tuning attempt. This is the two runs, and first we're looking at the decode throughput. So these are the baseline numbers, this column, and this is the tuned numbers for decode throughput. And so right away we can see that for a single user it's actually worse, but it has increased immediately for concurrency with 2 users and 4 users on both prefill lengths. The end-to-end time to first token, that's what TTFT is, if you remember episode 3, actually shows an interesting picture. The tuned version has actually done worse for the smaller prefill length. So actually it is like underperformed, but once the prefill length becomes larger, we start doing much better. So the time to the first token increases dramatically over here. Okay. We just compared the baseline with our first tuning attempt. Let's see if we were able to push our first tuning attempt further with the second level of tuning that we did. So probably have to fix the file name over here. I think it's 3.6, and let's make sure conservative is this. Yeah, let's see if it works. Oh, wrong file name. So cat/tmp Quen. Okay, what's the problem here? Conservative is the one that's wrong. Okay, so it's 3.6, 35B, conservative, short, and what have I said? Okay. Let's get that name right. So it's 3.6 for the throughput and 3.6 for conservative as well. Okay. And here the situation looks different. For decode, it's improvement across the board. So these again are the baseline numbers, and these are the tune numbers, and you can see that we've actually managed to push the decode speed. But the prefill speed is a mixed picture. So it improved for 512 prefill length for a single user and 2 users, but actually performed worse when there were 4 users. And for a prefill length of 2048 tokens, it only improved for the single user. Okay, so this is probably a good time to start because we have introduced a lot of concepts over here. Let's quickly go over what we just did. The first thing was we built a mental model for continuous patching. So what it looks like for multiple users to hit an inference engine at one time, and the way in which the engine actually has to juggle the decode steps and the prefill steps of different users at different times and try to saturate the GPU as well as it can. And as you could see, it's quite a dynamic situation. It's not obvious what the best settings are, and it can differ a lot depending on the kind of workloads that you're dealing with. We introduced Llama Benchy, which is this really cool little tool to run these kind of benchmarks over. We introduced a couple of knobs with the configs. So if you look at our latest config, let's take a look. Configs, oh, sorry, projects, so configs. If you look at the baseline config, where we had a GPU memory utilization of just 0.8 and no other models set, versus what we had done for, let's say, the throughput config. Here we set the GPU memory utilization to 0.88, and we also increased the max number of sequences to 32 and also increased the size of the batch to try and improve performance. This is probably a good place to stop. We have started looking under the hood and seeing the moving parts of this complicated machine. And we've also started doing what the EXD is, the sort of the ambition of the EXD, which is to start with the kind of tools we use today, come up with an objective, in this case, tuning inference to have better performance, and then using our learning and using that to motivate what we need to learn. Okay. Next week, let's look at another dial that we have available to us to improve inference performance, and that's called speculative decoding. It's kind of cool. So see you guys then.